Are you interested in jet engine propulsion or rocket engine propulsion? Easy for me to say. This video is going to help you characterize and quantify the performance of a nozzle, which will lead you towards being able to quantify the propulsion characteristics of a jet engine or a rocket. And so this video is the last video in Chapter 6 called Nozzle Efficiency. And it is similar to, let's see, what have we covered? Turbine efficiency, compressor efficiency, pump efficiency, and finally, nozzle efficiency. So what is a nozzle in the first place? Well, I've given you some, in Chapter 4, gave you some examples of a nozzle and also had a sketch, a basic nozzle. So you have to think of it as a converging device, very simple device, right? No moving parts, no shaft coming out. Now, for nozzle efficiency formulation, we're going to consider that these nozzles in the sketch and also these photographs, they're fully insulated, so there's no heat transfer from the nozzle surface to the surroundings. Now, certainly, obviously, with the sketches and the photographs, you see that no work is done by the nozzle. These nozzles are not lifting a weight. There's no shaft coming out. Also, we will consider that we've got our system as one inlet, one outlet, of course, as shown, and it's steady state, steady flow process. And so what's the objective of a nozzle in the first place? Let's see. The objective of a nozzle is to maximize the kinetic energy at the outlet of the nozzle. And so in examples, both of these are rocket nozzles for missiles. And so the kinetic energy, the more kinetic energy you have at the exit, the more thrust you have to push the missile through the air. This nozzle would simply be hooked up to a compressed air source in your shop or in a workshop or a machine shop, and your objective is to get the highest kinetic energy, velocity, leaving the nozzle in order to clean up your space, to move sawdust or shavings around on the floor and get them connected or collected to sweep up. Well, there's even a better example. So here's our shop floor nozzle, but some very good examples here photographically of trying to maximize the kinetic energy output of this two-engine jet engine, and also to maximize the kinetic energy, or in other words, basically the thrust of this Hellfire missile rocket. So let's imagine, let's go to our shop floor nozzle. You recognize, of course, that P1, the supply pressure of your nozzle is going to be higher than the exit pressure in the nozzle. If you could measure the pressure out here, do you see that the pressure out here, just outside the nozzle, that's atmospheric pressure, right? And so this P2, the P2 at the outlet plane of the nozzle is going to be less than P1, and it's going to be above the surroundings pressure. Okay. Well, let's see which one. So if you have a choice of process 1 to 2, either isentropic or actual irreversible adiabatic, which do you figure is going to give you the highest kinetic energy? I think you know. So we've got two choices. We're going to pick a reversible adiabatic nozzle, or we're going to pick a irreversible adiabatic nozzle, both insulated. Which is going to give you the best output kinetic energy? Common sense tells you that the best kinetic energy is going to be the reversible adiabatic nozzle, and this leads you to being able to define nozzle efficiency, because you know that it's got to be less than 100%. It's got to be less than 1.0. That now is common sense for you. So I hope that you can kind of come up with a conceptual definition of nozzle efficiency. And so here's our definition. So right out of the book, but I've made it bigger, nozzle efficiency is defined in terms of a kinetic energy ratio. So of course it's got to be less than 100%. So we've got in the numerator the actual kinetic energy at the outlet state, state 2, divided by the isentropic kinetic energy at state 2. So what will a TS diagram look like? We've got no heat transfer. We're fully insulated. So I think you see that based on entropy production rate and other good reasoning, you can see that S2 for the irreversible situation to actual, the entropy has got to be greater than the isentropic situation. And so you've seen, I'm showing this very simply because typically our nozzles are dealing with an ideal gas like air, for example, or exhaust gas or things like that. So a pretty simple looking sketch. And I'm delighted that at least in this video, I've got my isentropic and actual states labeled properly, so I don't have to go offline and change that. Well, let's come up with some specifics about nozzle efficiency. Okay, of course, that's not N nozzle, that's Greek letter eta. Said that a couple of times before, haven't I? So kinetic energy, well, it's simply 1/2 V squared at state 2 actual divided by the isentropic kinetic energy, 1/2 V squared at state 2 isentropic. Now, you and I both see that these 1/2s can be canceled, right? So you could actually take those halves out of the equation and you've still got your expression for nozzle efficiency, but I want to be true to your textbook. And there it is. There's the screenshot of your textbook, equation 647. And see, we're near the end of chapter 6. And so they preserve the 1/2 on both numerator and denominator. Notice how I'm a little different than the textbook nomenclature. Notice up here in the numerator, it just says V2 squared over 2. In my world, I call that V2 actual. And in the denominator, the textbook calls it V2 squared over 2S. But that's for isentropic, and I call it I. But you get the idea of how that would be handled. Let's say you want a little more background on nozzles. And so I remember I did, I hope you remember that I created a video back in chapter 4 on how to make first law calculations, first law of thermodynamics, open system, steady state, steady flow, how to make those calculations for a nozzle. And so this is kind of a results-oriented thing that I hope you can remember. I wrote out, so back in chapter 4, I wrote out the first law of thermo for a nozzle, steady state, steady flow, one inlet, one outlet, left-hand side, Q dot in and W dot out were both 0. So left-hand side is 0 equals M dot times a big bracket term. I can divide the M dot out, get rid of that, okay? I got rid of potential energy change term, right? Because this is just a nozzle. And a rocket nozzle can fit in your hand. So you get the idea that there's no change in potential energy. And so the important point all the way back in chapter 4 is, by the first law, H2 minus H1 exactly equals the kinetic energy change. The enthalpy change, outlet to inlet to outlet, equals the kinetic energy change, inlet to outlet. And that's an important conclusion all the way back to chapter 4. And you're going to use that in your calculations. So let me try to step you through a typical approach for dealing with nozzle efficiency. So unlike turbine, compressor, and pump efficiency, nozzle efficiency is rarely given. It is typical that you're asked to determine nozzle efficiency from certain given information. And so typically the inlet conditions of a nozzle, pressure, temperature, and velocity, are typically known, or you're able to find it. Okay. One thing I didn't put in my notes is you're also typically given P2. Typically you have pressure at state 2. So what you do is the first thing you'll do is you're going to analyze process 1 to 2A if you're given the outlet velocity. Okay. And so I do see that, again, I didn't put it in my notes. It says you're going to use the first law and the continuity equation, if you know the mass flow rate, to find V2 actual. You're going to use the first law. So that's coming back to me now. That's where the first law that I just wrote down. Let me go back a slide, refresh my memory. We wrote the first law for any, and so we've got H2 actual minus H1 equals V2 actual over 2 minus V1 actual over 2. And the chances are good that you're going to have P2 and perhaps T2. Okay. So that's the way you're going to solve for. You're going to analyze your actual process first, and you're going to solve for V2 actual. Okay. Then you're going to analyze the isentropic process. Okay. So you're going to use constant entropy fundamentals, S2I equals S1 and H2I, and the first law to determine V2 isentropic. That's going to be basically the only unknown. But do you see then so when you use the first law to analyze the actual process, which you did in chapter 4, okay, that gives you the numerator kinetic energy term. Once you analyze the isentropic process, that gives you the denominator V2 isentropic term, and that leads you then, once you know the nozzle efficiency definition, that way you can determine the nozzle efficiency. Now, the devil's in the details, so I just sort of talked through how you would approach a problem. I've created for you in my example problems open systems playlist numerical worked out problems for nozzle calculations that show you how to determine nozzle efficiency. So I hope that helps. So I'd suggest you go and have a look at nozzle calcs, really to go through the nuts and bolts of making a nozzle efficiency calculation. So typically the nozzle analysis approach is determine the actual outlet properties based on the information that's given to you. If you have pressure at state 2, you're able to study the isentropic process. That gives you enough to determine the actual kinetic energy, numerator, and the isentropic kinetic energy, the reversible adiabatic kinetic energy, denominator, and that leads to determining the nozzle efficiency. Well, amazingly, covered a lot of parts. Chapter 6 was a very wide-ranging chapter. It had a lot of theory in it. And then we kind of evolved from theory into applications. The applications were, how do you calculate little s2 minus little s1? A lot of details for that. You've got phase change substances. You've got ideal gases. For ideal gases, you've either got constant specific heat or variable specific heat. And then finally, we looked at real world equipment. We looked at turbines, compressors, pumps, and nozzles. So real applications in chapter 6. A lot of material and a lot of hard work on your part. The good news is that chapter 6 sort of represents a little bit of the finish line relative to theory and the introduction of governing equations that are general governing equations. And the rest of the course is basically going to be applications of the fundamentals in those first 6 chapters. So you've invested a lot of hard work in mastering the understanding of our thermodynamic principles. You've mastered the continuity equation. You've mastered the first law of thermodynamics. You're getting more familiar with and mastering the second law of thermodynamics. You know how to analyze closed systems. You know how to analyze open systems. And so the rest is some more hard work, but it's all applications. And it is my hope that as you're developing your interest in mechanical engineering, your interest in thermal, fluids, heat transfer topics, that you will get some level of enjoyment out of working through the applications problems throughout the rest of the semester. So I hope you've gotten something out of these sets of videos, and I hope that I'm encouraged to go ahead and keep doing some summaries for these applications chapters as well.